Okay, welcome back. Another advent of code in Clojure. This one was a pretty straightforward problem, and I think this is going to be an interesting one. Not because the solution was, it's really in a way kind of similar to a problem we did a couple of days ago, the simulation problem. But we're able to do a couple of interesting things in Clojure. Now, again, I don't know how idiomatic I am because I just am a hobbyist in Clojure. So please feel free to chime in, anyone. But I think it's some kind of cool stuff. So looking at the problem, where we are, and I already completed it a little bit before. Basically, you have a ship and a location, and you follow these instructions: north, south, east, west, left, right, or forward. And you have to essentially find a new location. So it's really, it sounds pretty straightforward. The input looks like this, so a little bit of parsing going on, but it's a single letter and then a number, so not too bad. And then we just have to follow the instructions. So let's take a look. So we'll do our usual. We are in our namespace. I'm going to do a cider jack in. And switch to the namespace once it comes up. I'll just leave the misspelling. And what we'll do a little bit differently, I really should have done this before, is, let's actually, well, I'll start by writing it. And we'll start with, now let's write it as a function. Load data, and it'll get a file name. And just because, we keep doing this in every problem, so we're going to start with the file name. We'll turn it into a resource that we've done all before. We will slurp it, and let's just start with this, and we'll do load data sample12.dat. And okay, so that's our data, so we can test it as we go along. Split the lines, and then what we want to do is we want to, if we run this again, we want to break it apart. And so we'll go back to regular expressions here, and we'll want to map this over each of the lines. So we'll run this on each of the lines. And we'll take the first item out of, we'll use reseq for regular expression sequence. And the first one will be a capital A through a capital Z, and that's it. And it'll be followed by one or more digits. Pass in the parameter. And that should be that. Run that. And oh boy, a little bit of a problem there. We will split the lines. Grab the first of reseq. Oh, right, I have the space in here, which I don't want. Still no good. That should do it. So what are we doing wrong? What are we doing wrong? Oh, right, it's not A through Z. It's the choice amongst, it's not A-Z as the pattern. I have to do that in the square brackets. And there we have it. So now we have our three pieces. So we're going to want to do another map on that. And we'll just pass it a function. We will destructure it. We don't care about the first item, just the second and the third. And what we'll do is we'll return a list where we take the keyword of that second item, and we will do a read string of the third item, which will convert it into a number. And not quite right there. And there we go. So we have now our instruction: forward, north, forward, right, forward, etc. And what we can even do is we can say, define our sample to be load data sample12.dat, and we'll say data will be load data and that'll be a day 12.dat, just so I don't have to keep coming up here to change it. Now for this problem, we're going to have our ship, and the ship is going to be moving around. So the ship is going to, we want to represent the state of the ship. So we'll say the ship has a position, and it starts at 0, 0. And the ship also will have a direction, which will be 0. So that is our state. And the way we're going to do this is we could just kind of do a loop through this, if you would, if you were doing this in any other language, and just kind of like, if the command is this, do that. If the command is north, do the north stuff. If the command is left, do the left stuff, etc. Or if you were doing this like in Java or Python with classes, you might make a class for your ship and have methods to do each of these. But we're going to do it a little differently. So we're going to set up a couple of things. We're going to define a few values. I'm just calling these values because these are going to be the values for, east will be -1, 0. That's just the way we'll use the grid. West will be 1, 0. North will be 0, 1. And south will be 0, -1. So this way we can just look up. We can, no source file. Got a little mistake in here. All right, these are square brackets, because I don't want to call these as functions. I want them to be vectors. So that way, if I can, if I'm going east, I can just call out that -1, 0 to represent my deltas, my direction in east. Same thing for west, north, and south. I also want to represent my turns, or my directions. And 0 is going to be east, 90 degrees will be north, 180 degrees are going to be west, and 270 degrees are going to be south. And the reason I'm doing this is because this way, when I'm turning left, right, up and down, not left, right, no, left and right, if I'm at 0 degrees, if I turn 90 degrees one way or the other, I'll get one of these 4 values, and then I can convert it to an east, west, north, or south, and then look up the value in vals. So I've kind of got all my parts here, and then what we're going to do is we're going to exploit some cool Clojure. You can also do this in other languages, like you can do this in Python or JavaScript or a lot of other languages, but I think it's kind of cool, which is the first thing is we can make these anonymous functions. So if I say function f of x is plus x3, and I run this, it returns a function. Now I could, of course, put it into a variable and then run it. And that's the same thing as doing a defn. Defn is just a shorthand for that. But I can also do this. I can return it and just run it like that. I can, and that way I'm just getting that function and passing in an 8. So this is cool, this idea of this anonymous functions that you can just dump down. And so what we're going to do is we're going to make a set of rules for part 1. And let's do this on the next slide. So our rule for east, if our rule is east, we're going to want to do a function. And what that function is going to do, now the first thing we're going to do is get the parameters to that function. And we're going to take in a state and the option of, of how far we want to go east. So for example, north 3 down over here, we want to pass the 3 into it. So we're going to destructure using the dictionary or hash table destructuring. And we're going to get the keys. And the keys we're going to get the position and the direction. So those are the 2 parts of our, out of our state. I don't think we're actually going to use the state. So that'll be our first thing, and we're also going to get the option, how much is it going to be, and then we're going to want to do something in the state. What we're going to want to do is for east, we want to modify our position by moving east option times the east direction of -1, 0. So what we're going to do is we're going to calculate, and the way we're going to calculate is we're going to map the plus function. The way this works is if you have two, let's say 1, 2, and 10, 20, if we map a plus on these, it'll add the corresponding elements. So we're going to want to add two things. We're going to add from our position, we're going to want to add to that, basically we're going to want to add the second list, the deltas. So we'd want to add the e's, but it's not quite as simple as the e's. We want to add another map, and I'll explain this in a second. I think that's it. Yes. So let's see if that's everything. So if I say rules, and this should be rules part 1. Rules part 1, we're going to get E from rules part 1. Sorry, I can't write. Get E from rules part 1, and that returns a function. And if I run this function, the first parameter into this function should be my state, and then the second parameter for the function would be, like, let's say east by 10. And a little bit of a mistake. What did we do wrong here? No rules 1, it's rules part 1. What? I do have rules part 1. Persistent vector cannot be cast to a class. So let's see, we got a little mistake in here. So we can figure this out. Let's first look at E of vowels. Okay, so that's okay. And that E of vowels is going to be put into that map. And opt should be fine as a parameter. I think I did pass it in as a parameter. Oh, I didn't right, I'm not passing that in. I'm passing in just the 10, just the option. And there we go. That has the effect of moving us 10 in that direction. To break down these parts, the E of vowels is just a way of doing a lookup in a dictionary. You can do it like a function. But what this is doing, times opt, mapping it on this list. So it'll basically say map times on option. Option was 10, and it got into the list -1, 0. Sorry. And it multiplies that 10 by each one. So if we make this, let's say 1, 2, 3, it'll multiply each item by that. So basically, this is going to do the complete east thing. So that's the same for north, east, west, north, and south. And I'm sure there's a clever way of like condensing all that down to one thing. I just don't know what it is, and I didn't bother to take the time. But we still have a couple of other options to do. In addition to these 4, we also have to happen, which one should we do next? We can do forward. And the way forward works is, again, it needs a function. So the beginning of this will be the same. So we'll destructure the position and the direction and the opt. But what forward is going to do, and I'm just going over to the my other window here to see, it's going to move the ships in its direction. So it's almost the same. Not quite the same, but almost the same. What it's going to be, it's, oh, and this is not quite right. What we want to do is we want to put this into state. We want to associate into state based on the key position. What that does is that will modify the state. That will put it back into the state. So if we have I don't think I reevaluated it. Let's go back up to here. When I did this, it just gave me back the new position. What I actually want to do is associate into state into that position, and it puts that into that key in the dictionary state. Now, it's not changing the state, it's returning a new state, but that's all right. So basically over here, we want to, again, associate into state position. So it's the same thing so far, but it's going to be, we're going to add to the position, and once again, we're going to map times the opt percent. But the difference here there we go. The difference here is we're going to first look up what our direction is from the state. So if it's 0, 90, whatever, convert that to the north, south, east, west by looking that up, that get dir is dir. And then that's going to be our direction vector. So now if we use forward, it's going to move us forward in the direction that we're facing by that much. So now 2 more of these to go. And so that's going to be, what is it going to be? Left and right. So left is going to be, again, the same thing to begin with. So left is going to be the same thing to begin with, but the difference between left is we're not changing the position, we're changing our direction. And the direction is going to be very simply is going to be the direction plus however many degrees that we have in our command, and then we're just going to mod it by 360. And if we go right, it should be the same thing, but we subtract the direction. So these are our rules. These are all of our rules. Let me just make this a little smaller. I don't want to, oh, that should be okay. I hope that's not too small, but I wanted to try to get this mostly on 1 line per. So these are our rules, so we can just use a dictionary lookup to call the appropriate function. And this, now we're at a pretty cool point because we can solve this in practically a one-liner. And what we can do is we can use Clojure's reduce or Lisp's reduce. The way reduce works is it accepts a function and then a sequence. And what it does is it applies, what it'll do is it'll apply the, if you don't give it, if the function just takes 1 argument, it'll apply plus 1 and 2 into a result, then that plus 3, then 4, then 5. But what reduce actually does is it actually takes a function in 2 variables. And the first variable is the state or your accumulator, the thing you're building up. And then the second thing is going to be the item from the list. And then you give it, well, the function itself, why don't we just say the function will just be plus the accumulator item. Now, then we can give it a first value for the accumulator, and why don't we make it 10, 100, and 1000. Close it off. And little wrong number of args, reduce that, plus accumulator item. that closes the function in my parentheses, right? And that's 210, or let's make that 1,000. And but if we change our starting value to, let's say, 5, it starts it out at 5. So reduce is nice. So what we have is we have our commands. What's the bigger one? But sample is our commands, and we have state, which is our state. So if we basically say, let's do a reduce, and we're going to reduce, we're going to get a function which takes, which is going to take our state, and then it's going to have a command and an option, or rather, let's say a rule and an option to that rule, and I'm going to destructure that. So that's going to be our starting point of our function, and then we're going to run the function rules part 1, so we're going to look it up of the rule. So this is the same thing that we're doing before, we just did the order differently. We're going to pass into it the state, and we're going to pass into it the option. And I hope I have, that should be there. And then we're going to start with our initial state. And then, well, let's do this as a threading macro, because that way we can do it a piece at a time. So we'll start with our sample. And then we'll put it through this reduce. And we got a little bit of a problem here. Let's see what our problem is. And you know, again, this is I've written this before, but it's effectively live. Check our state. Check our sample. Okay. So we're going to want to reduce. That runs the rules. That closes our function. We're going to start it at state. Rules part 1. And notice that may have a little mistake here. The position is -11, the direction is 0. So we're not doing, we don't seem to be doing all of the rules. So let's just double check and look at this. So east goes east, west goes west, north goes north, south goes south. Well, let's try this. So let's do take 1. And that looks okay because our first rule is, if we look at sample, is to go forward 10 and we're starting out going east. Let's take the second rule. That's okay. This might actually be okay because then we move north 3. Let's take the third rule, and the third rule is going to be forward 7, so that's actually okay. The fourth rule changes our direction to 270. I think that's correct. And our fifth rule after a fourth rule, oh, our position went back down to 0. So we have a mistake in here. So let's go again. To 3, we're okay. We're at -17. The fourth rule is the rotate, and the rotate messes up our position. So we got a little mistake in there. So the rotate right, we want to associate in state the direction and then the new direction, and that should be okay. It should not, unless we're not passing state. Oh, right, I have to pass the state into the function, right. So let's fix this. Right, we have to actually, so it doesn't go to the global state, we want to pass the entire state so we can use it as a single thing. And so there we go, let's take 5, and that happens to be the right value. So we don't want to take anything from that. So now we can turn this into a full solution. Let's pull out the position. Now we're going to want to take the absolute value. So I'll just use the math abs library from Java. And then we can apply the plus. And that should be our answer. And if we run it on our full data set, we have an answer. So that's pretty much that. So part 2 of the question becomes a little interesting though. For part 2 of the question, then it says, well, we actually have a waypoint. And the waypoint starts a little bit off from where we're at. So it starts, I think, 10 units to the east and 1 north, it's saying. And then north, south, east, west don't move us, they move the waypoint. Right and left don't rotate, don't turn us, but rotate the waypoint around us. And then forward moves us with respect to the waypoint. So let's see how we can make those changes. So the nice thing here is, well, we can start, we now need a waypoint as well. So let's add a waypoint to our state. And our waypoint is going to start 10 off of us. If we're starting at 0, 0, the waypoint is going to start at -10, 1. And if we rerun this, just want to make sure that that doesn't mess anything up. So now we need our part 2 rules. So we'll just copy these over. Now the first change is we are also going to want to read into here, we're also going to need our waypoint. So let's get the waypoint in as an additional, an additional destructure so we can get to that easily. Now, if we think about this, the difference here, north, south, east, and west, let's see, these are going to modify the waypoint, they're no longer like forward, right, and left will do what forward, right, and left are going to do. But the north, south, east, and west are going to modify the waypoint. And the thing there is, it's going to do the same thing as it did before, but it's going to modify the waypoint against the waypoint's old coordinate instead of so that should still all work fine. If we run it, it'll be harder to test because we don't have our data. But basically, it's the same thing as what we did before, but before, instead of changing the ship, here we're taking the old waypoint and we're moving the old waypoint. So now the next one is going to be forward. And forward is kind of interesting because forward basically is going to be, what are we going to do? So we're going to change our position. So we're going to add to our position, but what we're going to do is we're going to map times opt. We are going to multiply the option times, let me just think about this for a second, times the waypoint. Yeah, that should do it. Okay, so now right and left are the last two that we have to do. And right and left, I wrote some notes for, because I always forget. We can just do a rotation, and I always mess up my sine and cosine. So a couple of functions. First degree to radians. So we want to use sine and cosine. We want to use a transformation to do our rotation. And so since cosine and sine are calculated in radians, we want to convert our degrees to radians. And then we also want to have and we actually don't need the, I think we need just the x and the y. So the first thing we're going to do is we're going to say theta is going to be degree to radians of degrees. And then our x prime is going to be minus, and I wrote this down because I always get the order wrong. And then y prime is going to be plus of the multiplication of y and math cosine theta times x math sine theta. So there we have our let. And then we just want to return math round x prime and math round y prime. Close that off, close that off, close that all off, and that should be that. And now we are really almost done here, assuming that I wrote everything right. And again, I've written this before, I'm just rewriting it, and I've got a couple of notes here, but that's why I'm not testing this so much, and I'm just hoping that I do it right. So what we're going to do here, though, is when we change, when we do our rotate, what we're going to do is we're actually changing the waypoint, not the direction. We're actually not using the direction in this. And the way we're changing our waypoint is we are associating the state in the waypoint. We are going to rotate our position, or rather our waypoint. We're going to rotate our position, and in this case for the, what is that? That is left. It's going to be -1 times whatever the option is. And for here, it will be rotate the waypoint times 1, whatever the option is. That should do that. And then we should hopefully be basically done. So we'll take our sample and we'll put it through the same reduce. Rule and option. So we're destructuring it again. And then we're going to do rules part 2 for the part 2 rules of rule on the state with the option. And that's going to get sample in that. And if I type that all in correctly, I did not. Reduce function state option, that destructures it. We're in rules part 2 of the rule, state option. Oh, and I want to give it an initial state. And so that looks pretty good. So we've reduced. We are going to now take the position like we did before. We are going to map math absolute value on it. Put that on a separate line. And then we're going to apply our plus, and that looks to be our answer, and data. And there we do have the answer. I'm just going to double check it to make sure. Yes, it is. So there you have it. So the cool thing here, what I really like about this is we just make a lookup table, and we just call the values. We're just calling it in the lookup table, and we're using that reduce, and it just kind of grabs the next item, reduces it into the state, grabs the next item, reduces it into the state over and over and over again. So I hope that this gave a little bit of some insights into some cool Clojure stuff, notably passing the functions, putting the functions in variables and calling them just out of a lookup table, and a little bit on this reduce. And again, if I'm not being idiomatic, or even if I am, leave a comment, let me know. That's how I will get better at my Clojure, and I hope you enjoyed this.